something to write on. We're going to give you practice problems in just a second. These are reminders. There aren't many of them. Tomorrow is the last day for retakes for Unit 7. Okay, you have to be done. You have until 3:45 now because I have to be up in the tutoring room until 3:45 tomorrow. So, got to be done before then, ladies and gentlemen. Otherwise, doesn't get done. Final exams for first, third, and fifth hour. They are on Wednesday of next week. 1 week from today, ladies and gentlemen. And then 2 and 4 are on next week, Thursday. Then you will be on your summer vacation, ladies and gentlemen, enjoying yourselves until we start again in the fall. So, questions? Okay. So, here are your questions for today. You got 10 minutes, ladies and gentlemen. Let's go to work. Yep, I'm sorry. Sorry.
Oh, why didn't you? I'm not going to do yesterday. I was so tired of the meat. Honestly, you kind of saw the same thing. I just did a bag of butter and I took a packet of this one and then give it one. And then if you want me to write my God, give me this one. Write it on the solid states. Because they're all copies. Little booty. Thank you. What's the practice test? Thank you very much. What's each one?
If you look at the very first day of notes on that periodic table where the family trends are, we use that to define one of the groups. One of the group names means salt former. So the part about the family and group trends, it is on there. Okay. So let's talk about this, ladies and gentlemen. But before we do, what I handed to you was one of 3 practice tests that I have for you. So the first thing I handed to you was 2 of these. The reason I gave you 2 of these is because I have 3 practice tests for us to do. So you will need both sides of one and one side of the other. This is what the answer key to your unit test looks like. Sorry, to your final exam. Just like this. Okay? Your job is to take and place the clues in the spot on this test where they belong. Now, I gave you a practice test here because my intent is to be done with everything tomorrow at the end of class, as far as the notes that we have to get through. And then that gives us Friday, Monday, and Tuesday to do 3 practice tests, which I gave you here. The problem is, I don't think you can do this test and me go over it in the same class period and be done. So I've given this to you so you can start looking at it. Take 10, 15, 20 minutes a day and try to fill out your sheet. Now, this is a little bit different than the clues I've been giving you because I do not bring the answers from your blue sheet into this. I simply use letters. So if you look at the first clue, it says elements A, F, K, P, U, Z, Z, E, E, and J, J are all third period elements. So you're not doing Davy, you're not doing Eastian, you're not doing homogeneous, you're not doing heterogeneous. You're just using these letters. But these are sample questions like are off the test. Now, obviously, we haven't gotten through everything yet. We'll do that today and tomorrow. So if you read a clue on here and it's like, man, he never talked about what it means to be electronegative, I will get through that before we are done. Okay? But the point is, ladies and gentlemen, this is something that you can look at and you can start practicing. I'll give you the second and third test. I'll probably give you one of them on Friday and the other one on Monday, so you can practice them before we go through them. And then I will go through them at the end of the day on Friday, at the end of the day on Monday, and at the end of the day on Tuesday. Or I will put videos online explaining where every one of these answers goes on this sheet. Okay? So that is my plan for you. Now, somebody asked me this morning, is this a hard test? This is a difficult test. It is not impossible. I have had scores of 100 on this from multiple students. I've also had scores of 8, 6, 12. Now, to me, if you get a score of 8, 6, or 12, you really have not been following along. Because there are going to be probably 10 clues that are simply third period alkali metal, heaviest noble gas, the element that is a family unto itself, the most reactive metal, the most reactive nonmetal, things that you should nail. There's enough of those that you should be able to do fairly well, at least at a start. But there are tougher clues as well. And this is not about memorizing this stuff. But what it is about is being organized and knowing where you wrote something down. So when it asks you for it being in the same period as the number of F orientations, you need to know where you have the number of F orientations written down so you can go to it and you can say, oh yeah, that's 7. Not memorize that it's 7. If you could, that is great. But you need to know where you wrote down what number represents an F orbital. How many orientations are there? How many electrons fill it? Because you should have that written down. And again, looking over that blue sheet, you don't have to memorize what scientist did what. But you need to be able to scan it quickly and be able to find somebody. Okay? So again, these are clues that hopefully you can find on your blue sheet. Okay? So, again, you're going to have to work hard on this test. You get 90 minutes to do it. It is quite a bit of reading. But you can do very well on it if you know what you're looking for. What I mean is every clue should tell you what element you are trying to place, and it should give you a period or a group, period and a group, or it might give you both of those in one time by telling you a certain spot on the periodic table, where the most reactive metal is, where the most reactive nonmetal is, where the lightest of all elements is, where the heaviest of all elements are. Those are certain spots on there. Otherwise, they have to give you a group and a period. And that's what we're doing here. Okay? So the most reactive metal is named after the father of modern chemistry. All right. Somebody tell me, who is the father of modern chemistry according to your blue sheet? What's his symbol? Da. Okay. Now, this is a clue where I'm giving you the period and the group in the same clue because this is one spot on the periodic table. Where is the most reactive metal? What? Group number 1, period 7, in the lower left-hand corner. Perfect. I'm sorry, I thought I unfroze it for you, but I must have froze it. Thank you. Questions? Okay. The element named after the scientist who did the oil drop experiment. Millikan. Symbol. MK. Please be careful, ladies and gentlemen. There are a lot of terms on here with M. Make sure you are getting the right symbol. It sucks to get it wrong because you wrote down the wrong symbol even though you knew what the answer was. Is the most reactive nonmetal. Where are more reactive nonmetals? Where are more reactive nonmetals? Closer to what? Closer to fluorine. Okay? In the energy level, that would be the same number as half-filled p orbitals. How many p orbitals are there? How many? No. There are 3. So if each one is half-filled, there are 3 half-filled ones. There's 6 electrons total in the P's. Half-filled means there would be 3. 1 in each because they fill singly first. Okay? So this is telling us period 3. Okay? This most reactive nonmetal in the energy level, that would be the same as the number of half-filled p orbitals. So the energy level would be 3. Where would be the most reactive nonmetal in period 3? Group 17, right under fluorine. You can't go to group 18. Why? Those are non-reactive. Very good. Yes, Tanaya.
So it's just half the number of electrons if you're asking for half.
Correct. If you're at, or it's the number of orientations. You can think of it that way too. The number of orientations are the number of half-filled orbitals. Okay, either way. The element name for the scientist who set up triads. Element symbol is dB for Dobereiner. Okay, is the lightest in the period with a -2 charge. Where are -2 charges? No, not group 17. Group 16. And the lightest would be where? At the top, period 2. Questions? This salt former, what does that tell you? Group 17. It is a halogen. That is what halogen means, salt former. Is in the first period where f orbitals exist. What period do f orbitals exist in? In the 4th. And is named after the scientist who found the electron. TH for Thomson. The element name for the scientist who created the law of conservation of mass. LA. Now, to be honest with you, ladies and gentlemen, this really better be the easy part of your clues. Figuring out who the scientist is. Because again, I'm not going to ask you who got his head cut off by the king. Who created the law of conservation of mass? Who gave us the law of definite proportions? Who gave us the law of multiple proportions? you should be able to get those, okay? Is a slightly reactive metal that is in the period with an equal number of metals and nonmetals. Okay, let's start with the period that has an equal number of metals and nonmetals. What period has an equal number of metals and nonmetals? No, one has all nonmetals. Okay, please think about this. How many groups are there? How many groups are there? How many groups are there on your periodic table? How many groups are there on here? 8. So, half metals, half nonmetals would be when you have 4 metals, 4 nonmetals. What period has 4 metals and 4 nonmetals? Period 4. Period 4. Okay? Now, the slightly reactive metal is one that I have not given you yet. Okay? Slightly reactive metal would be the alkaline earth metals group 2. Group 2. So, take out this periodic table, ladies and gentlemen, this one that has family trends and group trends on it. And let's put a little information on there. All right, here we go. By the way, sorry, before I do that, any questions on any of these clues other than the one that we're working on about the being slightly reactive? Katie? I'm sorry, run that by me again from the start. I'm sorry.
Like for the one that was equal number of metals and nonmetals, we should look at this periodic
yes, this periodic table. Now, the only time we're bringing in the regular periodic table is when yesterday we set up this. Yesterday we put, sorry, hang on a second. Yesterday we put this square in here and this square in here. I am going to give you a clue that talks about elements being next to each other but differ by 11 or differ by 25. Which means we are recognizing that there are D's and F's, but they are not part of this table. So everything is based on this table, okay? So, for example, the most reactive metal is down in the lower left. Now, here's the other thing. Are there exceptions to reactivity, being more reactive as you get toward that? Yes. We're not worried about any exceptions, okay? So, if I'm asking you about these two spots here, which one is a better or more reactive metal? The one to the left or the one to the right? The one to the left. Now, that may not actually be true on the periodic table, but we're not going to worry about exceptions. We're only worrying about trends and things, okay? So here we're recognizing that those S's and D, or those D's and F's do exist, but they're not part of this table. The other place we recognized it is in that clue where it talks about where F's first exist. That would be in the 4th period. They don't fill until the 6th. But again, they're not part of this periodic table. So out of these elements, this is the period where it is half metals and half nonmetals. 4 metals, 4 nonmetals. Okay? So that's what we're using. Good question. Any others? Yes.
When do the orbitals first exist?
Certainly. In the 3rd, D's exist. In the 4th, they fill. In the 4th, F's exist. In the 6th, F's fill. This is where those things exist and where they fill. Now, we don't mark it down, but what exists in the 1st energy level? S. What exists in the second energy level? P's. And they exist and fill in these levels. It is only the D's and the F's where they exist in one energy level, but they don't fill till a later. Okay? I'm listening. Period 4, it says that the D's are one behind. Okay? Questions? That means that even though they are 3 D's, they are filling after the 4 S's. So in the fourth period, that is the 3 D's. They are one behind the period they are in. In the fifth period, those are the 4 D's. They are one behind. And the F's, which don't start filling until the 6th period, are the 4 F's. They are 2 behind. So they are 2 energy levels behind where they exist to where they fill with the F's. Questions? Okay. Anyone need more time? Okay. Good. You were supposed to get 2 of the same sheet. That's what I explained earlier. And you were supposed to get 1 of these. Okay. So on here, ladies and gentlemen, here's what I am adding to group 2. I am adding that these are slightly reactive with water. And I am adding to group 1 that they are highly reactive with water. So that is a clue that I do use on the test. I talk about a family that is slightly reactive with water. I talk about a family that is highly reactive with water. Highly reactive will be the alkali earth metals. Slightly reactive will be the alkaline earth metals. Questions? Okay. Anyone need more time with this? All right. Keep these handy because we're going to fill in a bunch of stuff on them today. Okay? Bunch of stuff gets filled in on these today. So we are going to talk about trends of the periodic table, ladies and gentlemen. Patterns, things that we will ask you clues about. So first of all, ladies and gentlemen, the periodic table is separated into 2 kinds of elements. What are they? You're either a what or a what? Metal or a non-metal. So, now, here are some properties of metals, and this should be a review from you. Somewhere along the line, you should have learned this about metals. Metals are ductile. Ductile means they can be drawn into a wire. Metals are malleable. That means they can be pounded into sheets. They can be shaped into forms. Metals are oxidized in a redox reaction. That one you've probably never heard before. Oxidation means you lose electrons. That's what oxidation is. Metals like to lose electrons in a reaction. Okay? They are good reducing agents. If you are oxidized, you are a reducing agent. We will touch on this a little bit more in our trends in a moment. Metals like to lose electrons. Metals are shiny. Another term for that is luster. And they have a high boiling point. Now, please remember, I have a clue for you. And your clue is comparing calcium and gallium. They are right next to each other on your periodic table, even though they differ by 11, because that's the spot in the fourth period that we highlighted yesterday. And I may tell you the element for energy being released. What is the element for energy being released? Exothermic is more ductile than the element for energy being taken in. Energy being taken in is endothermic. So now what it means if it is more ductile is that it will be further toward francium, towards metals. Okay? So if we talk about something being more malleable, more ductile, that means it's better metal and it is closer to francium. So that is how this could play into your test. Questions? Yes?
Is non-ductile supposed to say that it cannot be drawn into wire? Because they both say the same.
Well, it says that they are not ductile. Ductile still means that they can be drawn into a wire, but by putting that, I guess I kind of maybe put it poorly here. What I'm saying is it can't do that. And what that means is to be drawn into a wire. Yeah, I could have done it the other way and said it cannot. I'm sorry. I guess what I was trying to do is define ductile and malleable again for you and say they're not this. Which means we use this term for nonmetals. They are brittle. They will break apart instead. Okay? Yes?
So that malleable and ductile just means you're closer to francium.
Malleable and ductile means you're a better metal. Okay? Again, we're trying to keep this simple. So if you are talking about elements that lose electrons, well, the ones that lose electrons easier are alkali metals rather than alkaline metals because they are closer to francium, which are better than the group 13 elements, which have to lose 3 electrons. So again, the better metals are always going to be closer to this spot down here. The better nonmetals are going to be closer to this spot here. And again, I'm not going to ask you to compare things that are not in the same period or not in the same family. Okay? So I won't do that to you. Okay? Now, again, as Katie pointed out, the properties of a nonmetal are exactly opposite the properties of a metal. Things that a metal is good at, nonmetals are not good at. Nonmetals cannot be drawn into a wire. They cannot be ductile. They cannot be malleable. Why? Because they will simply break apart instead. They are brittle. Nonmetals get reduced in a redox reaction. Well, wait a minute. Oxidized means you lose electrons. What do you think reduced means? Go ahead, Elsa. You gain electrons. Thank you. It is the exact opposite. Metals are good reducing agents. Nonmetals are good oxidizing agents. Metals lose electrons. Nonmetals gain electrons. Metals are shiny. Nonmetals are dull. Nonmetals have high melting or high boiling points. Nonmetals have low boiling points. Exact opposites of each other. Questions? Okay, so now let's talk about some more individualized trends. Okay, so here is our first one. Again, we have this down. The most reactive metal on the periodic table is francium. The most reactive nonmetal is fluorine. So that last slide, if you are a better metal, it means you're closer to francium than the other element you are being compared to. If you are a better nonmetal, you are closer to fluorine than the other element you are being compared to. And again, I would compare something like carbon and nitrogen. Which one is the better nonmetal? Carbon or nitrogen? Carbon, nitrogen. Nitrogen is. It's closer to fluorine. Which is the better nonmetal? Selenium or sulfur? Sulfur. It is higher up, closer to fluorine. Same thing here. Calcium or barium, which is the better metal? Barium, it's closer to francium. Aluminum or magnesium, which is the better metal? Magnesium, because it's closer to francium. Questions? Okay. Now, let's talk about atomic radius. What is radius, ladies and gentlemen? Come on, what's radius? 1/2 the diameter, meaning we are talking about what shape? Now, most people believe that an atom is spherical shape. A sphere, 3 dimensions, but basically a circle, okay? So that is what we are going to talk about. It isn't quite 100% accurate, but to simplify things, we will say that atoms are spheres. Which means atomic radius is how what the atom is. How large, how big the atom is, okay? It is technically, by definition, 1/2 the distance between two covalently bonded atoms. Because atoms don't really have a spherical shape, the easiest way is if two atoms bond together, we could say the size of them is 1/2 the distance between them, okay? But basically, atomic radius is the size of the atom. Okay. In a period, as you go across the period, the atomic radius of an atom decreases. The atomic radius of an atom decreases. As you go down a family, the atomic radius increases. So now, ladies and gentlemen, let's go to this here, and let's put that onto our table. Now, I don't care where you put this, okay? I am going to put it over on the side over here. Why? Because this trend applies to all of these families. Atomic radius, as we go down a family, increases. So the reason I put it on the side is it doesn't matter which family you are talking about. All 8 of them, as you go down the periodic table, atomic radius increases. Here's why. As we go down the periodic table, we add another what? So we go from period 1 to period 2. As we go from period 2 to 3, 3 to 4, we add another what? What do 1, 2, 3, and 4 represent? What? Well, we add another energy level. Where does that level go compared to the last one? Up. Outside it, making the atom bigger. So as you go down the periodic table, the atom gets larger because you are adding more and more energy levels. Parker, headphone, please, sir. Thank you. Now, on the back side of this, down at the bottom, I am going to put this because, again, this is for all of the periods. Atomic radius. As we go across the periodic table, it decreases. The atom gets smaller. Here's the reason. As you go across the periodic table, electrons are put into the same energy level. But yet the atom actually gets smaller. The only explanation scientists can give for this is that electrons are attracted to the what part of the atom? The nucleus, the positive. And as you go across the period, what happens to the number of protons in the nucleus? Really? It increases. One more proton every time you go across the periodic table. What that does is that pulls all the electrons a little bit closer to the nucleus. And so as you go across a period, the atom gets smaller and smaller. Okay? Questions? All right. So we have that trend written there, and we have that trend written on the other one, on the other side. All right. Next, we're going to talk about ionic radius. Ionic and atomic radius are different. Ionic radius is the radius of a stable ion configuration. A stable ion, meaning that for period 1, what ion will they all be? What's the charge on period? I'm sorry, I said it wrong. What is the charge on group 1 of your periodic table?
+1.
So they will all lose 1 electron. What is the charge on group 2? What is the charge on group 13? Ah, plus or minus 4. Which ones are minus? Non-metals. Metals are positive because they lose electrons. Non-metals are negative because they gain. -3, -2, -1, 0. So that charge is what they will be when we are talking about them being stable. Okay, now this trend is a little bit more tricky, so here we go. As you go across a period, the ionic radius gets smaller, just like atomic. It gets smaller, and again, the same reason. The electrons are more attracted to a more positive nucleus as you go across the periodic table. But what does happen when you're going across is you go from being a metal to becoming a non-metal. So, sodium, magnesium, aluminum all lose electrons, right? They lose 1, 2, and 3. So sodium, magnesium, and aluminum all look like what noble gas? No, it is not argon. What are they isoelectric to? They're isoelectric to neon. So they all lose 1, 2, or 3 electrons and they look like neon. They get smaller as we go across. Now suddenly we get to silicon. Silicon is not going to lose electrons. What is it going to do? How many? 4. Phosphorus is going to gain. Sulfur is going to gain. And chlorine is going to gain. And they will all look like what? Argon. They will all look like argon. That means, ladies and gentlemen, argon has how many energy levels? Neon has how many? 2. So, as you go across the periodic table through the metals, it goes down. The ionic radius goes down. But what happens when you switch to being a non-metal? It takes a jump up. Metals will always be smaller than non-metals in the same period for ionic radius. Metals will always be smaller than non-metals for ionic radius. Atomic radius, it goes down all the way across. But ionic radius, it takes a one-time jump as you go from metals to non-metals to a larger size. Okay? So we need to somehow capture that on this periodic table here. We need to somehow capture that here. So, okay, here we go. Ionic radius. As we go across the period, decreases until you get to nonmetals. Then there will be a one-time jump to a larger ionic radius. Okay? In the same period, atoms get smaller all the way across in terms of atoms. The size of an atom, being a metal, being a non-metal, doesn't matter for the atomic radius. But for ionic radius, it matters. It matters because you go down, 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 you hit a non-metal, you take a big jump up because you have another energy level, and then you start going down again. Okay? So within the metals, further to the right means smaller for ionic radius. Within the nonmetals, further to the right means smaller for ionic radius. But for a metal to a nonmetal, metals are always smaller than nonmetals in the same period. Always smaller. Question. What do you think happens to the ionic radius as you go down a family? It increases. Just like no exceptions, nothing like that. Ionic radius increases as you go down. And I hope you understand what it means when I draw this arrow here. I'm talking about going down the group, down the family. Okay? Questions? Okay. Now we're going to talk about something called electron affinity. That is the ability to attract and hold on to an extra electron. What atoms are great at this? What kind of atom wants to attract and hold on to an extra electron? Which are? Nonmetals. Nonmetals are good at this. What elements are bad at this? And noble gases. Okay? Metals and noble gases are not good at this. So this trend does not go into the noble gases. Okay? So as we go across the period, electron affinity increases because we go from being metals to being nonmetals. But do not include the noble gases. The noble gases do not want to attract and hold on to an extra electron. Okay? So again, we're going to start out by going across the period. Electron affinity. As you go across, increases. Do not include group 18. The noble gases are not part of this trend. So what family has the best electron affinity? What group number? 17 halogens. 17 are the halogens. Okay? Questions? So, what do you think is going to happen as you go down a family? It's going to what? It's going to decrease. Why? Because you're getting further away from the nucleus, it makes it harder to hold on to an electron. So the best nonmetal for electron affinity is what? Fluorine. Very good. Electron affinity as we go down. Decreases. Gonna move. Okay. So again, we just said as you go down the family, electron affinity decreases. Okay? All right. So now, electronegativity, ladies and gentlemen. Electronegativity is kind of similar to electron affinity. It is the tendency of an atom to attract electrons to itself when combined with other atoms. What atoms like to attract electrons to themselves when they combine with other atoms? Which ones like to gain? Nonmetals. Nonmetals again. Are the noble gases going to be in here? No, they are not. Okay? Now, this, ladies and gentlemen, we give a number from 1 to 4. 4 is a high electronegativity, 1 is a low. And it is relative. Meaning this one, really good, we're going to give it a 4. This one, really bad at it, we're going to give it a 1, and then we're going to give everything else somewhere in between. Okay? So, as you go across a period, electronegativity also increases. Okay? So as we go across a period, electronegativity increases. So electron and affinity and electronegativity again increases, but do not include group 18. So electron affinity, electronegativity, again, the best element for that, fluorine. What's the worst element for this? Francium. So what does this mean for electronegativity as you go down? It's going to decrease. So electronegativity as you go down, decreases. As you go down, it decreases. Please remember, at the end of the hour, I will put these out on the back table. If you miss something, you can take a picture of them and take it with you just in case. Questions? All right. All right, so we covered both of those. Ionization energy, ladies and gentlemen. Ionization energy is the energy needed to remove an electron from an atom or ion in its ground state in the gaseous phase. So basically, it's how much energy it takes to get an atom to give up an electron. What atom on the periodic table has the easiest time giving up an electron? No. Right? No. Right group, wrong place. No. Francium. Francium's the best metal, right? What do metals like to do with the electrons? Give it up. Francium has the easiest time giving up 1 electron. What element has the hardest time giving up 1 electron? Nope. What? Nope. Nope. Yes. Helium. Why doesn't helium want to give up an electron? Because it's stable. It's stable. It doesn't want to give up an electron. It's stable. So, ionization energy, as you go across a period, ionization energy goes up. It gets harder to give up an electron as you move across the periodic table. So, let's add that. I'm out of room down here on the bottom, so I'm going to put it under atomic radius. Ionization energy as we go across increases. What would happen as we go down a family? What element has the easiest time giving up an electron? So what happens to ionization energy as you go down? It decreases. It becomes easier. It becomes easier. Okay. Questions? So really what we're seeing, ladies and gentlemen, is that spot of francium and that spot of fluorine or maybe helium, they're kind of anchor points here. As you work toward them, again, things are going to increase or decrease. You're writing down what's going to happen. Okay? You're writing down what's going to happen. All right. Electron shielding. Okay? Electron shielding is, well, let's put the definition up there and then kind of explain it to you. It is the reduction of attractive forces between the nucleus and outer electrons by the electrons that are in between. So in other words, the valence electrons are attracted to the nucleus. But what gets in the way of them are the levels in between. Okay? So, for this one, as you go across a period, electron shielding is constant. Why? Because there are no more electrons between that valence shell and the nucleus. So it is constant as you go across. Okay? It is constant as you go across. So I'm going to put it over here. Electron shielding as you go across, it is constant. Okay? It is constant. What happens as you go down, though? Now think about this. As you go down, what happens to the number of energy levels? So now there are more levels between that outer electron and the nucleus. What will happen to electron shielding? It will what? No. It'll increase because there's more electrons between those outer ones in the middle, the nucleus. So electron shielding as we go down, it increases. Questions? We're good? Okay. Oxidizing agents. Oxidizing agents, ladies and gentlemen, are substances that cause another substance to be oxidized. Okay? So oxidizing agents are what gets reduced. And reduction was doing what with the electrons? Gaining or losing? No. Gaining. What elements like to gain electrons? What element is the best at gaining an electron? Fluorine. So the best oxidizing agent is fluorine. So again, on this periodic table this time, ladies and gentlemen, that spot for fluorine, we are going to take and put down that this spot, fluorine, is the best oxidizing agent. That is the best, sorry, I'm writing it above where you can see. That is the best oxidizing agent. So where is the best reducing agent? Francium. Francium is the best reducing agent. Francium is the best reducing agent down in the lower left.
So metals reduce and metals oxidize.
Remember, to be an oxidizing agent means you are being reduced. The opposite. To be a reducing agent means you are oxidized or you lose electrons. Okay? So being oxidized means you are being a reducing agent. Being reduced means you are an oxidizing agent. They are opposites of each other. Okay? Questions? And I did put in there that the worst reducing agent would be fluorine, but the best is francium, so hopefully you understand that the worst is at the other end of the table. Questions? Okay. All right. So let's talk real quickly about radioactivity here. Radioactivity is unlike any chemical reaction. It is not actually a chemical reaction. Radioactivity is when the nucleus of an atom will spontaneously break apart. And your atom will change into a different kind of atom on your periodic table. And the reason it changes to a different kind of atom is because during nuclear decay or radioactivity, the amount of protons in the nucleus can change. Okay? So when an atom undergoes radioactive decay, we are talking about an element changing what kind of element it is on the periodic table. But it is predictable what kind of element it will become, because there are three types of radioactive decay. The first is what is called alpha decay. And in alpha decay, what happens is 2 protons and 2 neutrons break apart from the nucleus of the atom. The alpha particle is 2 protons and 2 neutrons. By the way, anything with 2 protons is a what? What is anything that has 2 protons? A what atom? What has 2 protons? Come on. What has 2 protons up there? Which atom? It has an atomic number of 2. Helium. So what really happens is a helium atom leaves your atom. Now what that means, ladies and gentlemen, is if you had 84 protons originally, if you undergo alpha decay and give off 1 alpha particle, how many protons do you have left? You become lead. You move 2 spots back for every alpha particle. You move 2 spots back for every alpha particle. I am going to put that, ladies and gentlemen, at the top of this periodic table. This is not a trend of a spot or a family. This is just what happens. So I am going to put this, ladies and gentlemen, at the top of this periodic table up here. I'm going to put alpha decay. Lose 2 protons per alpha particle. Now, you could lose multiple alpha particles at the same time. But every time you do, you go back 2 spots on the periodic table. So if you are polonium, and you lose one alpha particle, you become lead. If you were to lose 2, you would become mercury. You keep going back 2 every time. Okay? Questions? Now, the next one is called beta decay. Beta decay, you gain 1 proton per beta particle. Now you may be asking, ladies and gentlemen, how do you gain a proton? During beta decay, a neutron in the nucleus of an atom breaks apart into a proton and an electron. Now the electron gets shot out of the nucleus because it doesn't belong there, but the proton gets left behind. So now, ladies and gentlemen, if you have something like francium, and it undergoes beta decay and gives off 1 beta particle, what does it become? It becomes radium right next door. And if you gave off another beta particle, you would become actinium. Okay? Questions? Okay. There is a third type of decay which is called gamma. Gamma, nothing happens in the nucleus, so we don't need to worry about it. Gamma decay there are no changes. The atom does not change. It stays exactly what it was. Okay? It stays exactly what it was. All right. Questions? Okay. Last thing, ladies and gentlemen. Okay? Years ago, when they were discovering elements, they would discover an element and it took some time to name them. Okay? So when they discovered an element and they knew where it went on the periodic table, but they had not yet named it, they used the prefix, and the prefix they used was Eka. E-K-A. Eka means 1 below. So, for example, ladies and gentlemen, before they named tellurium, they would call it Eka selenium, meaning it is 1 below selenium. So the prefix Eka in front of a element